Good evening, everyone. I'm Adrià Colomé. I'm a postdoc researcher here at the Instituto de Robótica and Informática Industrial, and I will be talking now about robot motion learning. Now, when I talk about robot motion learning, I'm referring to the learning of robot actions. So not that, not as we see in some applications where the robot is calculating a sequence of actions to achieve a certain task, but rather the motion of the robot and how the robot moves through these actions. So it's not about which object to pick from a table, but rather how to approach the object, how to pick this object, and how to move around with this object. So imagine the case of playing tennis, and in this situation, you imagine that the robot is trying to play tennis, and a ball is thrown to the robot. So the robot must perform a swing with the racket. So that motion, the strength that is applying, the trajectory of the arm and therefore the racket is what we are focusing on here. But moreover, we are focusing on this kind of robot motion learning in human environment, and this entails a lot of additional problems that we need to take into account. One of them is that we want the robots to be very easily programmable, so that anyone can program a robot and then can show a robot a certain motion. So traditionally, in the early stages of industry, they had an engineer that would, in a factory, that would go to these huge robots and that would program the motion point by point, okay, from here to there, to there, to there, and then this motion would be repeated and repeated. But then, if something would change, then they would need this engineer to go back and then do the same procedure again. It was time-consuming, it was costly, and it's no longer how we want to program robots since a few years already. The thing is, how can we encode robot motion in a way that it's suitable for, from a mathematical perspective, to encode data properly, to allow for changes, and also talking about dimensions. So having mathematical models that are not overfitting in some ways, because if we overfit, then we will then have problems with our models, because actually, if we want the robot to learn, then we will need the robot to generate new motions, so that the robot can explore freely, or in certain conditions, about the motion that we have just taught him. So if we have a motion characterization, a mathematical model that is too large in terms of dimension of the parameter space, then the robot will be unable to perform efficient sampling on this search space that he wants to improve the motion on. So this is something that we need to take into account. But then, of course, the sample efficiency for the robot to improve the motion that he has just learned. So in the case of the tennis swing, you can characterize the motion of the robot with some mathematical model. But then the robot needs to try to improve through experience, and if the robot needs to get a lot of the most information as possible from these samples that he will generate, because in some cases we can have many samples, many data for the robot to learn, but in many real robot applications it is not the case. So when there's only real robot executions that can be used for the robot to learn, then sample efficiency becomes very, very important, and any information that is lost in the process of learning is something valuable that we missed. In some cases, we can actually simulate part of the learning, learn in simulation, and then transfer this knowledge to the real robot that will adapt this prior knowledge from simulation to the real case scenario. But we cannot always rely on these situations. And of course, the the environmental circumstances change. So again, in the case of playing tennis, the ball can come from here, or a little bit up or down, or on the side. So the robot needs to readapt this motion that he has been learning to these changing situations, and that is very important, because otherwise we are again in the case of the factory, where we need to relearn from scratch if we cannot have a model that can readapt to changing circumstances. But again, we are talking about robots in human environments, so this entails things like safety control, because robots are very strong, are rigid, are metallic, and if they hit a person, they hit something, they can break it, they can hurt him, or anything. So we need to take control into account, and we need to take safety measures so that the robot doesn't hurt anyone. So within this talk, I will briefly introduce a little bit of kinematics and control, and then talk about robot motion learning, how to characterize motion, how are these policy improvements on robot motion learning done, how to be more sample efficient, how to adapt to changing circumstances, and a little bit of control, both in talking about kinematics but also in learning control. And starting with kinematics, of course, the first thing to do is to see what robot you're working with. In this case, we have been working for quite some years with anthropomorphic arms, which are arms that are similar to the in structure to the human arm, which is which has 7 degrees of freedom, same as this robot. Now, if the joint space is 7-dimensional, and we have we want to control the position of the end effector, or of the hand of the robot, then that is a Cartesian pose of 6 dimensions, the x, y, z position, and the 3 orientation coordinates. So this means that we are mapping from a 7-dimensional space to a 6-dimensional space, and doing the forward kinematics, which is the mapping from joints to Cartesian pose, that is relatively easy. It is so every joint position is mapped to a single end effector position, and so on. But the other way around, it becomes complicated, because, for example, in this case, we are mapping from a 7-dimensional space to a 6-dimensional space, and the inverse mapping will have like infinite many solutions for most of the Cartesian pose points that we want to convert to joint positions. In fact, in the case of this robot, we will have several one-dimensional manifolds of solutions for each end effector pose. So this is something that we always need to take into account. So know the robot that you're using, know its kinematical structure, know how to map from one thing to another, and know what are the redundancies, and meaning the degree of freedom that is free when you do this inverse kinematics. Again, another thing that needs to be taken into account when doing manipulation, in case that you want to do dual arm manipulation, is how you configure the 2 arms. So basically, when we want to manipulate, we want to have the arms cooperating in a way that they can have a higher performance in the manipulation area. But also, if we mount 2 arms together, we need to comply with the mechanical restrictions, physical restrictions that the 2 arms impose on us. So basically, their weight, their how they move, how they must be mounted, etc. So that is something that also needs to be taken into account. Okay. And another very important issue that I was talking about is in human-robot interaction, we don't want like rigid behaviors like in this video. So here we see that we push the robot a little bit, but then it has quite a lot of backlash. So this is at a very low speed, but it's something that we do not want, because at higher speed, then the backlash can be much stronger, and then can be hurtful for a person. So in order to, sorry. So one way to do this kind of like software control is by using feed-forward controllers, in which we apply a control torque that is an inverse dynamic model of the robot plus a PID compensator that compensates for the modeling errors and the deviations from the desired position. And this inverse dynamic model is basically a model of the dynamics of the robot. And we have this desired trajectory that we want to track, and the feedback of the robot gets into the controller that applies this controller action on the robot that is joined with by the external forces. So if we take a look at the robot dynamics equation, then this is what we have, where the Q is the position, velocity, and acceleration, and we have this inertia matrix, the gravity terms, and the controller action. And these are easy to have because we either get it from the CAD files or by the weights of the components of the arm, or the controller that is what we send to the robot. However, there are other terms like the Coriolis and centripetal forces that are a little bit more complicated to get, or even the friction. And with the friction, we have to be very wary because friction is a very relevant term usually in robotics, and it is usually very hard to model. And so a lot of problems come from friction, and it is kind of one of the main factors that limits the capabilities of robot for being compliant in its behavior. Again, we also have, for instance, we have an acceleration that can be very noisy. And why is so? So some robots, not all the robots have accelerometers, not all the robots have direct velocity readings. So some robots only have position encoders. And in such situations, you have to be very, very careful, because if you extract an acceleration from there, then you will be differentiating twice the position. But by differentiating twice, imagine that you have a time step of 1 millisecond. So if you differentiate the position, the error on the position encoder will be multiplied by 1000. But if you differentiate again, then this error on the position encoder will be multiplied by 1 million. So basically, the acceleration noise that you will have will be the position encoder noise multiplied by 1 million, and the reading will be basically a lot of noise and a hidden acceleration signal that you cannot actually read. So you have to be also very careful with this situation. And if we build a suitable controller by building an inverse dynamic model of the robot, so modeling all these terms on the left side of this equation, we can apply the controller and combine it, for instance, like with state observers to, for example, evaluate forces that are occurring during the manipulation or during motion. So basically inferring the external forces that are applied on the robot, but also while having a compliant behavior of the robot through motion. Now, this also allows for doing more like human robot interaction tasks. In this case, what we do is we show a robot to kinesthetically. And that is one of the ways of teaching robots like friendly programming of a robot. So it's basically putting the robot in a gravity compensation mode and then moving it. So when we are moving the robot is recording this data, and then it encapsulates this data it has recorded into a mathematical model that can then reproduce the motion, or as I mentioned before, and I will talk about it later, change this motion a little bit. But actually, using these controllers that are compliant, we can even substitute the mannequin for a person, and still the robot will be able to perform and with safely the motion that we wanted. This requires also some additional safety features, like limiting all the torques that we apply, like things, and also things such as making the trajectory time of the robot is dependent on the error. So that if the error is too large because someone is pulling the robot, then the trajectory will slow down. And also, for example, preventing this backlash that I was talking about before. So now that I've introduced a little bit about robot kinematics, robot control, let's talk about robot motion learning. But in order to talk about robot motion learning, Let me first introduce you to reinforcement learning. So in reinforcement learning, most of you are already familiar with it. Traditionally, you have a set of states and actions and a policy that decides which is the best action to take at every step, at every state. And this policy is taking these actions based on some function of reward. And but in the case of robot motion, it's more complex. So imagine the case of for example, the typical case of a robot in a simulated grid that he can go left, right, in front or backwards. Then the number of states is finite. The number of actions possible is also finite. But in the case of robot motion, it is not. So everything is a little bit more complex, and it needs to be reformulated. So in this case, the state space can be the joint configuration, the poses of the robot, etc. And the actions will be the motor or acceleration commands. They can be also the desired trajectory. And we have a control policy pi, which is the one that, given a state, decides which is the best action to take. And we have also transition probability, which is given a state and that we apply certain action, what is the possible outcomes of applying these actions at this current state. And this can depend not only on the robot dynamics, but also in external factors. Of course, if we can gather a sequence of states and actions, and that is a trajectory of a robot, also called rollout or path. And for building a reinforcement learning setup, we need a reward function that will tell us how good a motion a trajectory is. And this reward will usually consist on a terminal reward if the task at hand was achieved or not. In the case of the tennis swing, for example, it would be if we hit the ball to the other side and it fell into the square. And then you have like time-dependent rewards also. That can be like how much effort is being done by the robot, or how fast the ball is going, for example. But given these definitions, what reinforcement learning is doing is basically optimizing this guy here. So basically, reinforcement learning then becomes an optimization. So, and basically, this J here is the expectancy of the reward function given the policy. So if we find the policy that maximizes this thing, we will have the policy that on average gives us the best reward, because this is what this equation is giving us. And this is, in the case of robotics application, this is called direct policy search, because then we will have policies parameterized by a certain parameter space, and we will find the optimal values of these parameters for the policy to achieve this the best mean performance on execution. However, in reinforcement learning, there are some difficulties in robot motion. One of them is these high-dimensional states and action spaces that make it very difficult for the robot not only to explore with sense, but also to update the policies and to execute new motions that make sense. Again, there's real-time requirements, because we need to perform the actions in real time, and there is a cost for experimentation. So real robot executions, real-world executions are costly. Moving a robot is costly, not only in terms of robots that are very expensive, but also it's time-consuming. And so we have to limit the amount of real robot experimentation that we make to a feasible value. And classical reinforcement learning methods are more difficult to apply in this robot motion because of these value function approaches that are more difficult, because they are continuous spaces, and we cannot. It's very hard to adapt to these situations. Therefore, what is often used is movement primitives, which are ways of characterizing motion. Now, I will talk a little bit about different options when characterizing motion in a way that are useful for learning robot motion. When we talk about characterized motion for robot learning, we could say, okay, anything can do. Let's just build, for example, a spline representation of motion. Splines are continuous, are differentiable. Everything is easy, but there is a problem, for example, with the splines, and that is that the parameters on splines have restrictions between each other, so we cannot change one parameter freely, and that is a desired property that we want for learning robot motion, but because we want motion characterizations that are generative, and generative in the way that they can generate new samples, but we generate these new samples by generating random by randomizing our probability distribution. But if we randomize something that has restrictions, then it becomes more complicated, because we cannot randomize a single parameter, but we have to randomize several parameters and their restrictions that are nonlinear. So one of the most used over the last almost couple of decades movement representations are dynamic movement primitives. Dynamic movement primitives are simple to understand in the sense that you set the desired acceleration of the motion as a goal attractor, which is a second order critically damped dynamical system, plus a certain excitation function. And this excitation function, F here, is a weighted sum of Gaussians. And this weighted sum of Gaussians has these Gaussian kernels that are the ones here, and these Gaussian kernels have fixed centers and widths. But we have these learning parameters omega that are the ones that actually define the motion. And we also have this x of t here that is a decay function to make sure that this excitation function tends to 0 when the trajectory ends. So with this setup, it is very easy to find these learning parameters for every trajectory by doing least squares or other approaches. And given a robot motion, we can fit these parameters and then build a distribution and generate new samples and try to do more trajectories. Dynamic movement primitives have some advantages. They are kind of a compact representation. They have good rescalability properties. We can change the goal of the motion and it will adapt very smoothly. It is intuitive. It is an intuitive representation. The parameters. If we increase one parameter, we know that we are increasing the acceleration at a certain part of the trajectory, and it is a policy that is linear with respect to the parameters. So remember that in this direct policy search for robot motion learning, the policy is the probability distribution on these parameters that define the motion. However, the dynamic movement primitives have some problems, like there is a singularity on this rescalability of the goal, and it is very difficult to assign buyer points in the middle of a trajectory. Also, if you have noisy data, it can corrupt a little bit the computation, the fitting of the weights, because of these least squares fitting that it's often done. And there are some ways around this problem, but then it becomes more complex and complicated. And another way of representing robot motion is to use what's called probabilistic movement primitive. So imagine that you have several motions of the same task, but you can observe that sometimes, like when doing a motion, doing a part of the motion, you are moving a little bit vaguely, but it is when you cross certain area that you become like very precise and you go through that point, and then you become vague again, and then you are more precise again. So with probabilistic movement primitive, if you have several trajectories that can show you this behavior, you can encode such properties. And what they do is somehow a little bit similar to the dynamic movement primitives, in that is a linear model of a linear model. And here we have that the state vector can be position and or velocity, and is the weighted sum of some kernels or basis function times some weights plus a system noise. And the good thing is that for every trajectory we get a vector of this omega, and then from these omegas we can build a probability distribution on this omega, and this probability distribution on this omega will be our policy, and it can be directly mapped to map the mean and variance of the trajectory distribution that I was showing in the previous slide. So probabilistic movement primitives have some nice advantages also. The trajectory is built at the position and velocity level in this case, and we don't have acceleration coming around, which is sometimes very noisy in these cases. But the main advantage of probabilistic movement primitive is that it allows for all the probability operations. It allows for conditioning, it allows for product. So playing with probability distributions, so we have, imagine one set of trajectories with one distribution, another set of trajectories with another distribution. We can make the product of these distributions, and we will have like the intersection of these distributions, or we can blend from one trajectory, gradually convert it to another. And also, the authors of the original paper provided with a model-based stochastic controller that could track these variance over the trajectory. However, this stochastic controller could suffer from numerical stability in case that our policy variance was not fully conditioned. And also, a very important thing that we'll see later is that when building such kind of motion representation in which we consider the variance over different trajectories for the same task, we require that these trajectories are aligned in time. So basically, we need to rescale the motions so that they are consistent in time. Another way of representing motion is by using Gaussian mixture models. Now, in Gaussian mixture model is a weighted sum of Gaussian distributions. And in this case, for example, we see in this picture we have we have data points of two components, and we build two Gaussian nodes, and within the equation we will have this pi k, which will be the probability of each one of these nodes. And then what we can do is condition to one or to another. So basically, if we have two variables, we can express the probability distribution, which is the same, but just separating the two variables, and then we can condition one to another or vice versa. So basically, if we have one of the variables is the time and the other is the state of the robot, then given a time, we can extract the probability distribution of the robot state. Also, one could think, what happens if there is a bifurcation on the data? So one trajectory splits into two different options. So in this case, it could happen that this method is averaging between the two bifurcation and ends up giving a mean point that is in the middle. But you can also have variants of this Gaussian mixture modeling that allow for choosing one of these bifurcations, and so it works nicely. So Gaussian mixture model again allow for this kind of bifurcation. It's also very useful for conditioning variables and so on. You can add more variables that you can see, and Bayer points are not that much straightforward as with probabilistic movement primitive, and it also, depending on your representation of what you're representing in X and Y, you could also require time-aligned demonstrations. Now, another way of representing motion could be with Gaussian processes. In Gaussian processes, you fit a function with a mean and a kernel matrix that represents the covariance between the data points that you have. So what the Gaussian processes build is this kind of profile where in the situations, in the parts of a motion, let's say that where you have a lot of data, these red dots, then you will have a small uncertainty on what the robot is on the robot motion. But in those areas where you do not have much data, then you will have more uncertainty. This is also very useful because you can then apply what's called Bayesian optimization in order to send queries and say, okay, I do not know anything about this part of the motion, or I know very few, but I think that it could be a good region for exploring. So you can bias and do what's called active sampling, which is that you no longer randomly generate samples, but you actually generate samples that you know that will provide you information. Now, I have talked about different motion representations, but what is common in some of them is the time alignment and the importance of these time alignment properties. So imagine that you have these trajectories on the upper left corner, and you build a probabilistic movement primitive with them. So what you would get is the lower left corner plot. And you see that if you align the trajectories on the upper right plot and you build a probabilistic movement primitive, they are both very different. So there is a very large difference, and the one correct is on the right side. So aligning time is sometimes forgotten, but it is very important in case you use one of these kind of models. So always think about it. If you have several motions that you have to compare, make the comparison coherent with the time. And then, so given to have these motion characterizations, then how can we learn? How can we make the robot learn? How can we make the robot improve what we have? So we have taught something to the robot. Now we want the robot to autonomously improve what we have taught him. So usually we have some demonstrations that generate an initial policy or reference motion, and then we have some exploration parameters. We build this policy that is a probability distribution on the parameters of the motion representation, and then we have the robot randomize and generate random motions within this distribution. And then after some of them, we can then reevaluate our policy, update these parameters, given that we have evaluated the outcome of these executions. And how is this done? So I was talking about this direct policy search, where we optimize our friend here, the expected reward given the policy. So the best policy is the one that on average gives us the best reward. And these policy search methods can be divided into model-free, where we do not model anything about the system or the reward function, or model-based. And in model-based methods, we can model the dynamics of the system, we can model the reward function, or we can model both of them. And model-based methods are often more complex, but can be more sample efficient in case that we are very limited in the amount of samples that we can generate. Also, we can plug, if we have prior knowledge of the dynamics of our system, we can plug it in and then have also better sample efficiency. And policy search methods can be divided into three main groups. One of them is to use policy gradient methods, in which we compute the gradient of this J here with respect to the policy parameters, and then we update the policy by doing a step on the direction of this gradient. There is also a lot of literature regarding how to compute these policy gradients, how to make them unbiased, how to make them the best for learning the policy, also about learning rates. And actually policy gradients were also very popular for deep reinforcement learning, and are still very popular for deep reinforcement learning. There is also other approaches like expectation maximization approaches, in which we convert the problem into a statistical inference problem, where we do not have learning rates, but the thing is that they are computationally expensive, and sometimes we need to solve very complex systems of equations. And also there are information theoretic approaches in which are based in information theory, basically that the robot doesn't want to lose information when updating its policy. And a very one of the typical methods in this subfield is called relative entropy policy search, in which imagine that the robot is generating samples of a task, and every sample is evaluated and has is associated reward. If the robot has performed a motion 20 times, and there are 2 of those times that the reward function was very high, but the other the reward was very low, what the robot would do if we didn't pay attention to that would be just to average between those 2 very good samples and forget about the rest. But this is a very greedy behavior that we do not want, and we do not want not only because it's forgetting about the rest of information, but also because it will change the policy too much, and changing policy is being changing too much a policy on a real robot scenario can become dangerous, because you get to somewhere that might be unknown. And so this relative entropy policy search, what they do is to first to maximize this integral here, which is nothing more than, again, the expected reward of the task given our policy, subject to this bound plus that the policy is a probability distribution. What is this equation in the middle? It is the it is a bound on the Kullback-Leibler divergence between the new policy and the old policy. So basically, we limit the amount of change within the policy, and this allows us to control how greedy we want the policy change to be. Now, there are other things that we need to take into account. So one of them is policy representation. Another one is how to update the policy. I showed you an example of a policy search method, but when we have a limited amount of data, we encounter a new problem. Most of these methods that I was showing then recompute the policy by getting some weights associated to each sample, and then doing this and then computing new mean and new covariance of the parameters. But if we compute the covariance like this, or the unbiased covariance, what we see is that it is a sum of weighted sum of just rank 1 matrices, because these guys here are column vectors times row vectors, so they are rank 1. So if we add up n samples, so we have n samples and we add n rank 1 matrices, the rank of the covariance will be at most n. And if we have 20 samples, it is very easy that we do not have a full rank matrix, because in the case of the robot that I showed before, that it has 7 degrees of freedom, imagine that we set 20 Gaussian kernels per degree of freedom. That makes for 140 parameters in the parameter space, but we only have 20 samples. So the covariance matrix in the parameter space will be 20-dimensional, but it will be a 20-dimensional matrix within a 140 dimensional space. So that poses a new problem, that is that we cannot, so we are just forgetting about most of the dimensions, and we are limiting ourselves to what we have already explored a little bit. So we either need more samples to fill this covariance matrix, or we need smaller dimension in the parameter space. And okay, so for reducing this dimension, we can do we can work in latent spaces of the motion characterization. We can do latent spaces in dynamic movement primitives, probabilistic movement primitives, by projecting the robot's state into a latent space. For example, in the case of the probabilistic movement primitive, sorry, we'll go quickly, and we can, for example, reduce from so a walking behavior of which is 12-dimensional into a latent manifold of dimension 4, which is that can still map correctly the policy, and that we can use for learning to improve this policy. Also, we can use several types of latent space projections in different parts of a motion, and do like blending between them. That would also yield good results. In this case, I will show you an example of learning to fold a polo cloth, and what we are doing is working in the Cartesian space. So basically, we have 6-dimensional space for one arm or 6-dimensional space for the other one, and we placed the two arms accordingly to what we thought it was best, and with some optimization in the middle, and then we apply these compliant controllers, and we use different methods for different methods to the learning. And what happened is that, of course, the standard representation of dynamic movement primitives, as we had a few samples, was struggling a lot to learn. So first we did some demonstrations to the robot, and we decided who was the one who was going to teach the robot. It actually turned out to be me, and we kinesthetically teach the robot. This was just one motion, so we devised the variance heuristically, and from there on, as I was mentioning, the standard method was had too many parameters to explore, and was struggling a lot to improve the motion that it was learning. We were using a rooftop camera to evaluate how wrinkled the polo was ending up and how squared it was. And what we realized was that if we were doing this dimensionality reduction techniques, we could eliminate these irrelevant directions of exploration early and have a better convergence of the reward function. Also, we used different latent space projections, and that yielded also a little bit better results. But in general, what we see is that standard representation had too many parameters, and which is the red line, and it was struggling to obtain a good policy. Now, this is not the only way to reduce the complexity in terms of dimension of the parameter space for learning robot motion. If we know that the task at hand has some symmetry or geometrical properties that we can exploit, we can also take advantage of that. Imagine in this case, we were thinking that some tasks have some symmetry patterns between them. So we applied a master and slave behavior between the two arms with respect to a symmetry manifold. That could be a plane, but could also be a curved manifold. And then we using this master and slave behavior, we substituted all the parameters of the motion policy of the second arm by just the parameters of the symmetry manifold. In the case of a plane, it's just 4 parameters. So we went down from maybe 140 parameters, which are 70 plus 70, in case that we get 10 parameters per degree of freedom, and we have 2 robots and we're working on joints, and we have 140 for 2 arms, then we can go from 140, which is 70 plus 70, to 70 plus 4 parameters, and that drastically reduces the dimensionality, and can be applied in different scenarios. This showed to be very, very useful. Also, I will go very fast through this. We can use other nonlinear dimensionality reduction techniques. In this case, we used Gaussian process latent variable models, and Gaussian process latent variable models, what they do is there is a relation between Gaussian processes and principal component analysis, and that is that in principal component analysis there are stochastic variants called probabilistic principal component analysis, in which you can turn around the data matrix in a way that you end up by solving not to find the latent space projection from the data space to a latent space. So you don't optimize and find the projection, but you directly find the latent space values of the variables. So you do not find the latent space projection, but the latent space values. And this means that as you're optimizing for the latent space values, you can refine and push further the amount of dimensionality reduction that you're doing, and so end up in a smaller dimensional manifold. In this case, let me skip this. We applied this in learning robot motion in this scheme where we had some trajectory data, and this data was processed, and what we did was we projected into a latent space which is a much smaller dimensional, and we did the sampling and exploration there, and so we could also do Bayesian optimization in that latent space, which was 2-3 dimensional instead of 100 dimensional, let's say, and find the optimal there and then project upwards. And this helps a lot on sample efficiency, because as I was telling, the amount of samples that we execute on the robot are something critical for learning robot motion. Again, another thing that I haven't talked much about, but it is very important, is that we want robots to be adaptable. And when I say adaptable, means that the robot needs to be to know to move to different locations within the same task. So in the case of the tennis swing, again, if the ball is a little bit upper, then we have to adapt to that motion. So what happens with that is then we need, so we can use similar motion representations, but we will need much more data. And again, this makes the dimensionality restrictions, the sample complexity, like even larger problems. In the case, we can also see this case in which we fit a mannequin here with 2 types of different food, and we have different contextual variables, which are the position of the 2 plates, the position of the head, which kind of food we are feeding. And for that, we can there are different tools to adapt to these changing situations. So some reinforcement learning methods already are adapted to these context variables, like in the case of the relative entropy policy search, you have the contextual version. But but I think that is also very useful is to add a context variable S that can represent anything that we can measure from the task and is influencing the task to the motion characterization. And then, so adding this, we can make the motion conditioned by this variable. And then, even depending on the motion characterization that we are doing, we can do probabilistic conditioning. As an example of this kind of applications, we combined these dimensionality reduction techniques in order to obtain this new variable in this feeding task that I was showing, and we made a Gaussian mixture model with this together with this context variable, in which we could also apply to character writing. Let me quickly show you a video here. So again, we would observe the data, and this is how we gathered the data for this problem. And we would then build this Gaussian mixture model, which would have 2 different tasks, so 2 Gaussian nodes, and we would detect this through computational topology in this case. And then, given a context that would be where are the plates, where is the head, and what kind of food we want, we could actually end up providing the food to the mannequin. Okay. And this was all by conditioning on the context variable. So it is usually very useful to plug these contextual variables in the motion characterization, and then make this dependence. Also, I think I will skip this. We applied this Gaussian process latent variable models for dynamic dimensionality reduction and dynamical models for doing cloth state estimation. Maybe let me see if we can. You probably don't see this. Let me share the screen again. Okay, I think you see this. So in this case, we're using this Gaussian process latent variable model in order to build a model-based reinforcement learning setup. And what we did was we project the whole state of this cloth mesh into a three-dimensional manifold. So basically, we could project all this data into very small manifold where we could do reinforcement learning. Okay. 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 Regarding control, another thing that we need to take into account is the representation of the orientation. There are several orientation representations, and they all present some problems when doing reinforcement learning. So basically, when we do reinforcement learning, we want the robot to generate new samples, and when we generate new samples, we don't want restrictions between them. So if we represent orientation with quaternions, then we will need to maybe project the quaternions into a three-dimensional manifold, explore there with our covariance in such three-dimensional manifold, and then project this upwards again to the quaternion space, because we do not want restrictions on generating samples. There are always there are some literature which they consider this problem and they tackle it. One approach to that is directly use Riemannian manifolds, but this also gets more complicated from the computational perspective and also the mathematical perspective. So as a conclusion, many factors need to be considered when learning robot motion. You need to know about the kinematics of your robot. You need to know about the control of your robot. You need to be sure that it will be safe if you cooperate with a human. If you place something that might be broken or might be hurt, then you need to pay attention to the control that you're using. Also, motion representation is really, really important for learning motion. And in order to improve motion through experience, you need to be adaptable to different circumstances. You need to be efficient with sampling. You need to take into account if your problem is multimodal, that is, it has several optimal points. And of course, take into account conditioning on the policies that you do. Take into account dimensionalities of the policies that you're working with and everything. And if you do all this, then you can end up having the robot learning something. So thank you very much for your attention. Now, if you have any doubt of comment, just let me know.
Thank you very much, Adrià. Do we have any comments?
Okay, it looks like we don't have much questions. So thank you again for your attention. And if you have further comments or like other doubts, or you want some references about some topics, you can write an email to me. What was your learning setup for the arm? Learning setup, meaning, can you be more specific?
Yes, so in terms of how was it set up, how did you track the, yeah, everything, and how did you then do the back propagation, and well, the whole learning cycle, basically. I'm kind of curious about that.
Okay. So basically, we in general, what we do in this case is that we first generate data. So we generate data for encoding some initial motion, initial guess. We can have someone demonstrate a couple of motions to the robot, either 1 to 15 motions, not much more, because otherwise it's not what we desire in ideally in a household environment or in a domestic environment. We don't want people like normal people to learn to teach a robot, like to spend too much time. But then we would feed some models. We have tried all of these motion representations that I was talking about, plus others, and we can also have, for example, synthetic initializations, like setting up some buyer points, initial points, some variances, and so on. And from there, we usually have some reward function that is in our case, we haven't worked too much on inferring an unknown reward function. So we usually assume that for the robot it is a black box, but we have a function that evaluates this reward function. But if you're interested in knowing this kind of reward function, this is called inverse reinforcement learning, where you would learn the reward function. Then, given the policy that is stochastic, the robot was trying rehearsing the motion, and then we were evaluating on this. With this evaluation, then the robot could actually update its policy, and this can be done with one of the classical policy search enforcement learning methods, or we also did Bayesian optimization with active sampling and so on. I guess this answers a little bit your question.
Yes, it does. Do you maybe have a public repo on that?
We have several papers about that. Well, if you look at my personal webpage at the ED website, we will see some papers about this topic, so you can see some of the experiments that we are doing.
Okay, I'll do some stalking.
Okay, thank you. Sylvester asks, what kind of continuous reinforcement learning method you were using? We have been using, as I was saying, relative entropy policy search and its variants. We have been using Bayesian optimization. We have been using policy improvement with path integrals, policy gradients, but mostly different kinds of policy gradient methods, also information theoretic approaches. Exactly. Could you explain about the model-based reinforcement learning that is quite extendable for training new behavior, for instance, in complex robots such as humanoids? A book about it. Well, actually, my thesis is published. It's published as a book, but you can probably find my my PhD thesis. You can have something. Well, you can probably find something that might interest you about that. But also there is a survey. I think it's CSIC-UPC. It's I think Konstantinos Chatsiliggeroudis, I think it is, wrote a survey on policy search, on this kind of here. It's called a survey on policy search algorithms for learning robot controllers in a handful of trials. I will link the title on the chat. I think that is a relatively recent and very interesting survey on the topic, I would suggest. And regarding the model-based reinforcement learning, yeah, it is quite a large topic. For humanoids, so in model-based reinforcement learning, you have well, you can have several types of model-based reinforcement learning. You can model different types of things. You can model the robot's dynamics, or you can model the manipulated objects dynamics. You can also model the reward function that you expect, etc. And you can do that for active sampling. So it is a whole. I think it is a whole topic. And also, you can, in the reference that I wrote in the chat, I think you can have they also talk about it and give more references. So it is a very interesting read. I suggest you have a look at it. Also, sorry, Tien was asking, can the robot deal with different type of shared size? If yes, how? So at this point with cloth modeling, we are testing different things. So for example, we are regarding control, we are using model predictive control in order to track the robot position and, well, the cloth position when manipulating it. And so first of all, we need to have real-time model predictive control plugged into the robot and so on. So after that, we will see how it generalizes to different types of shirts and size. But in simulation, we did some testing also using meta learning. Probably you're familiar with it. And meta learning is now becoming very popular because it's actually focused on generalizing knowledge to tasks that share some properties with the task that you have learned, but are not exactly the same. So I think that is the way to go to work on meta learning if you want to generalize with different type of clothing for the task. Also, then Sai says, I'm interested in the dynamics of the robot to have some dynamic behaviors like jumping, running, squatting, and flips. Well, this reminds me of Boston Dynamics robots. In Boston Dynamics, they have been working on this kind of like jumping, running things that they do. The work that they do is really outstanding in terms of control of the robot. I think they probably have like super robust, super precise dynamics learned dynamics from the robot they are using, and they probably have methods to like compensate for the changes in the dynamics through time that the robot experiences. But modeling the dynamics of the robot is not an easy thing. Nowadays, if you have like simulated data, you can learn the dynamics with things like deep learning, or if you have less data, you can use a Gaussian process-based approach, because one of the differences between deep learning and Gaussian processes. So the main difference for applications is that deep learning is really, really useful when you have a lot of data. But it so often struggles when you don't have much data, and then Gaussian processes are kind of the other way around. Gaussian processes are really useful because they do not they keep most of the information of the data, but the more data that you have, the larger that you have to invert the matrix, and then everything gets computationally expensive exponentially. And there are come arounds by using what's called Bayesian Gaussian processes, in which you set some called inducing points, so to reduce this problem. But yeah, you can use these methods to try to model the dynamics of the robot. In the case I was presenting, the robot was dynamically relatively simple, but still the friction of the friction was quite problematic, because the friction is not just like a viscous friction, static friction. There are magnetic frictions there are motor frictions, that are frictions on the cables of the robot that are transmitting the motion, etc., etc. Could you explain which approach is better, model-based or meta-learning, for learning new behaviors or extending current behaviors? So I think so. Of course, that is a very interesting question. I would say it depends on the task itself or the class of tasks that you're working in. There are probably tasks in which model-based reinforcement learning will be able to generalize in a certain way, but at some point you will need to do some meta learning. There is I think it's called a hindsight experience replay. It's a paper regarding meta learning, and they try to make like more and the authors also try to make like one-shot improvement on the generalization of tasks. My thesis is downloadable. It's not among the publications on ID. Okay, if you are interested, you can send me an email and I will send you a downloadable link for it. Okay, is Riemannian manifold representation computationally efficient? That is a good question. I haven't, so far I haven't personally worked with Riemannian manifolds, but I foresee that depending on your application could be a bottleneck. But probably if you check the papers, I think I linked one from Noémie Jacquier about Riemannian manifolds for orientation representation. They were working on also symmetric positive definite matrices as a representation of variability and so on. So maybe check the authors and see. For the attendees, okay, that's that link is probably. Well, it's probably a link to one of the documents I mentioned. Okay, so thank you for your very interesting questions. If you have further questions or you think that you need some references or so on, you can write an email to me and I will try to send you the reference. Okay? Okay, thank you everyone.